Alas, our last lecture. But don't worry, this is just the primer, right? These ones don't even count. These are the pre-lectures. So, much more to come. But, this last one, ooh, I moved my lamp. I'm like so much more visible now. Okay. General and specific solutions. So we're just rounding it off now. So we have our homogeneous solution. We have our particular solution. And we know that the general solution is simply the sum of those two. So we're going to knock that one out right away. And then we have one left, the specific solution. So that's all we've got, and our method will be complete. So we're doing that in this lecture, and that is it for the primer. So we'll finish up today, or now. It's all been one day. I'm not sure if you could tell, but it started out earlier, and then, yeah. I prepared all the notes beforehand, so just recording the lectures and eating food and taking care of Niles. That's been my day. So anyways, general and specific solutions. We posited in lecture 2, which for me was this morning, that the general solution to the ODE of equation 1.1, which, let's flip back there, this guy, right? Same equation we've been dealing with the whole time. So we posited in lecture 2 that the general solution to the ODE equation 1.1 is the homogeneous plus the particular solution. So great. We've been expecting that. We've been waiting for that to happen. It has finally happened. We have not, and we will not prove this, but simply propose that it's true, and use it. Working through a proof of this from, for instance, your differential equations textbook is of some value, so I do recommend doing that. You may have already seen it and you may be comfortable with it, but if you're not, you might consider going back. It's so hot. I don't know why. Summer is, well, I do know why. It's only like all the scientists who have been telling us why it's so hot. Anyways, so, great. So we have the general solution. So of the 4 solutions, homogeneous, particular, general, man, that was the easy one. We just added the homogeneous, particular together. Boom. So finding it is trivial. What type of object is the general solution? Well, the particular solution contributes only determined coefficients. Remember, we determined what the coefficients were, so we ended up with a complete solution at the end of that. However, the homogeneous solution contributes an unknown constants Ci, so where n is the order of the system still, or order of the differential equation, which is actually the same. This means Yg inherits those constants and therefore is a family of solutions. Just like the homogeneous solution, it's a family of solutions. So if you choose different values of C, for each C variant we have a different solution. So it's a whole family of solutions. This leads us to our final step, applying the initial conditions to find the specific constant Ci and thereby our specific solution Y. That's what we want, right? We want a solution that is unique. And in order to get a unique solution, we need to apply the initial conditions. Applying the initial conditions is simply to subject the general solution to each of them. For instance, if we have 2 initial conditions, such as, say our initial time is time 0, we could have it be anything, but let's say it's 0. It's typically 0, so y of 0 is equal to 2. There's one initial condition. We're saying that the output at time equal to 0 is 2. And another initial condition might be dy dt, so the time derivative of the output at time equals 0 is equal to 0. I mean, these are just arbitrary. I just chose these as an example, right? From these, we can construct two algebraic equations by taking the general solution and applying the first initial condition. So yg at time equals 0 has to be equal to 2. Okay, that's one of the initial conditions being applied. That gives us one algebraic equation. And if we apply the other initial condition, which was dy dt, so yg now, we plug in, we use the general solution. We apply this initial condition to the general solution. When we evaluate that at time equals 0, we should get 0. So these two equations would give us a system of algebraic equations from which the two unknown constants C1 and C2 from the homogeneous solution can be solved. So that is the method. It's really as simple as that. We're sort of at the end now, so we have the general solution, and the specific solution comes from applying the initial conditions to get it. People call the specific solution different things, and I actually don't have any alternative terms to give you, but I'm confident that you called it something. You might have just called it the solution, yeah, there are other terms for it, but we'll call it the specific solution, which I think is a pretty good name for it. It is also consistent with the textbook that we'll use in Mechatronics and System Dynamics by Rowell and Wormley. So, and this is generally following what they do too. They use a similar method to solve differential equations in their textbook. So, example 5.1, a general and a specific solution. So find the general solution for the equation. So we have a second order linear ODE with forcing function a cosine omega t, where a is some constant and omega is 5 radians per second. Apply the following initial conditions to obtain a specific solution. So y of 0 is equal to 3, and dy dt at time equals 0 is equal to 0. Those are our initial conditions. Here's our forcing function. So remember the existence and uniqueness theorem that we discussed in lecture 2 said that if you have your linear ODE and you have a forcing function and you have initial conditions, you can solve for a unique solution, and one exists. And not only that, but we've also shown you how to solve for that. So all the pieces together now. So first, let's find the homogeneous solution. So I'm gonna number our steps here. If I remember to. I didn't do it in my notes, so I'm gonna try. You guys can't shout across the internet through time. Well, if you can, let me know. So first, let's find the homogeneous solution. So let's do A. What do? Characteristic equation. So, looking at the differential equation, we have a second derivative of y with respect to t. Actually, let's stop for a second. I wanted to mention something. Notice how we've always had 1 as our constant for this highest derivative term. You might think I'm pulling a fast one on you and giving you just cherry-picked problems. However, I mean, that's true. But if this was, say, 4, okay, we could simply divide the entire equation by 4, which would leave this as 1, which is what we're looking for. And this would become 5/4, this would become 6/4, and this would become f of t over 4. So you can always make that coefficient 1. You can't make multiple coefficients 1 necessarily, but you can always make one of them 1. So we choose that one to always be 1, just for the form that we've written in the general form. So if you want to use the formulas that I wrote down, you do need to do that every time. We could have just used in the general formula an here. Would have had to write an an in some equations. That'd be fine. You can do that too if you'd like. Yeah. So in any case, I thought I didn't mention that before. So we were about to write the characteristic equation as part of our homogeneous solution, right? So we had the second derivative of y with respect to t, so that gives us a lambda squared, plus 5 first derivative, so lambda to the 1, or just lambda, plus 6, and then lambda to the 0, which is 1. And that is equal to 0, right? So the roots of that can be found by factoring, probably the easiest in this case, or quadratic formula, or don't use a root solver for this. If you use your calculator for this, God is watching. God. Anyways, lambda 1 and 2, so lambda 1 and 2 are equal to -2 and -3. Okay, great. C. Both roots are real, right? So we can use the easier form of the homogeneous solution, which just says that the homogeneous solution is the sum, and we'll just write them out separately, of two terms. So there's two roots of the two terms. So C1 e to the lambda 1 t plus C2 e to the lambda 2 t, where we now know lambda 1 and lambda 2 are. And that's our homogeneous solution. Great. 2, we need the particular solution. So what's the first step? We need to look at the form of our forcing function. And we actually have a sinusoid just like we had in the last one. So if you remember, we could look back at the table. I think it was table 4.1. That a cosine omega t corresponds to a guessed particular solution of k1 cosine omega t plus k2 sine omega t. So that's the particular solution that we'll guess. We'll also check, we should check, the test value, which, as you may recall, is j omega for this case, and omega comes from the forcing function, which is 5 radians per second, so j5. And we see that there aren't even any imaginary components in our roots. There's no way one is j5, so we're good. Good. Okay, so we have this particular solution that we propose. The next step is to, so, A, propose. B, this is step 2 from lecture 4. Yeah, lecture 4. So, step 2 was to plug into the differential equation. And this time we don't need 5 derivatives. We only need 2. But let's do those 2 explicitly. I've just found that writing them out is useful. So let's say first computing the derivatives. We have dyp dt is equal to, we already did this, derivative of cosine's negative sine, negative k1 sine, oops, I dropped the omega. That's what happens when you get in a hurry. Sine omega t plus k2 omega cosine omega t. Great. Second derivative of yp with respect to time is equal to, derivative of sine is cosine, pick up an extra omega, cosine's negative sine, and also another omega there. Great. So now substitute into the ODE. So we need to look up here. Well, let's do the same thing that we did before. We really don't want to write out this in long form. We see once again that we're going to get cosine terms and sine terms in each of these on the left-hand side, and on the right-hand side we'll also get cosine terms. I did sinusoid, a sinusoid for the forcing function because it's harder. If you do the constant, which you'll do in the homework, the exercises, it's much easier. So the sinusoid's harder, so I thought I would do that, but in any case. Great. So the second derivative is first, and then we have 5 times the first derivative plus 6 times just the particular solution equals f. So let's write that. So let's do the cosine terms first. So let's see, how much room did I give myself? A lot of room. So let's say down here, I'll do the cosine terms first. So the first one is negative k1 omega squared. So negative k1 omega squared. Then we have, my notes battery is running out. My phone. That could be fun. Okay, we'll just have to do it. I think we can. I believe in us. Believe in me. Okay, the next cosine term, k2 omega, but we also have the coefficient from the equation, right? So we've got 5, right? So 5 and then k2 omega plus 5 k2 omega. And then the next term, we have a k1, and that one has a coefficient of 6. So 6k1. And then cosine, on the right-hand side of the equation, we have whatever the forcing function is. And it has a cosine, and it has this coefficient a. So the right-hand side of this equation is also a. The sine coefficients are essentially the opposite. So we have this negative k2 omega squared to start us off. There is a pattern that emerges, but I caution you from getting too enamored with just seeing the patterns. Negative k1 omega, so negative 5k1 omega, and then finally we have plus k2, plus 6k2, right? Excuse me. And then the forcing function, the right-hand side of the equation, has no sine term, so its coefficient is 0. So we set the left-hand side sine term equal to 0 because the right-hand side is 0. Okay. Once again, 2 equations, 2 unknowns. Solve any way you want. I used elimination, actually. In this case, it was pretty easy. So let's see. I want to make sure I'm still substituting. Okay, C. Solve for K1 and K2, which gives us K1 equals, and I'll actually write this out, negative A omega squared minus 6 divided by omega to the 4th plus 13 omega plus 36. And if we substitute in omega equals 5, we get negative 19a divided by 986. And we have K2, which is equal to 5a omega divided by omega to the 4th plus 13 omega plus 36, which, if you substitute in omega equals 5, you will get 25a divided by 986. Great. So we've got our K1 and K2. We have determined our coefficients, right? So that was our particular solution. We know that it was a particular solution because we could find a K1 and K2 that solved this system of 2 equations and 2 unknowns. And now we know what those coefficients are, K1 and K2. So our particular solution, whoa, reminders. My sister's getting married in Portland in 2 days, so I've got to go to Portland tomorrow. Another reminder. Don't worry, Maria, I'll be there. Okay. Great. So we have our particular solution. We proposed it. Turns out it is a particular solution. And K1 and K2 we have solved for. So all that remains is step 3. The general solution, which is simply yg of t equals yh of t, the homogeneous solution, plus, it's an h, yp of t, the particular solution, which I'll write it out, but I have to give myself a little bit more space than that. I'll write it up here. Equals C1, so here's the homogeneous solution part, e to the, I'll plug in lambda 1, so negative 2t, plus C2 e to the negative 3t. Kind of breaking my rule here and plugging in some numbers a little early. It's not my favorite, but you know, sometimes you play a little fast and loose with your principles. You should never do that. You should do it a little. It's kind of important, I think. So cosine, and then I'll put the parentheses, 5t, and then plus 25 sine of 5t. So this is the particular solution. K1 and K2 I plugged in to this guy right here, and 5 is what omega is, and I just factored out the term with a in it, and that's what I got. So good. Niles, he's protecting me. Okay, step 4. General solution, specific solution, right? The first step, apply the initial conditions. So we were given that way up here, y of 0 equals 3, and dy dt time equals 0 equals 0. So we apply each of those to yg. So the first one is yg of 0 is equal to 3, right? Which gives us this. So let's plug that in. Well, I don't need to use the same line. The other initial condition, of course, is dyg dt at time equals 0 equals 0. So those are the two equations that we're going to write now. So the first one is, it's just exactly this with time equals 0 plugged in, right? So let's do it. Let's do C1 e to the 0, it's time is 0, plus C2 e to the 0, plus a over 986 times negative 19 times cosine of 0 plus 25 times sine of 0, which we know is 0, right? And on the right-hand side, so we say the initial condition is that plug in 0 to all of this, and it has to be equal to 3. So that's the first equation. The second equation is that, so the time derivative. Time derivative is just going to drop, so time derivative of e to the negative 2t is just negative 2 e to the negative 2t, right? So we're just going to pick up a negative 2, c1. It's going to be e to the 0 again. And then we've got negative 3 that comes out for the second term, c2 e to the 0, plus a over 986 times, and then we've got derivative of cosine is negative sine, so we have a positive 19, and then we've got the chain rule, right? So the 5 comes out, so times 5 times sine of 0 plus derivative of sine is cosine, so we're gonna get the 25 still times 5 times cosine of 0. That one has to be equal to 0. So we can simplify this, so I'll do that simplification step so you can see that it's really a pretty straightforward set of equations. So e to the zeros just go to 1, right? So I will say this implies that C1 plus C2 plus A over 986 times 20, so times negative 19, right? Because cosine 0 is 1, sine 0 is 0, equals 3. And the other equation is negative 2c1, negative 3c2, and then we've got plus 125, so we'll do A over 986 times 125 times 1 equals 0. So this set of equations, 2 equations, 2 unknowns, C1 and C2, solve. This one's real easy to do with elimination. Solve. So B actually is solve. Foreshadowing. Solve for C1 and C2. And I used elimination here. You can use whatever you like. I got C1 equals negative 2A over 29 and plus 9. And C2 equals 3A over 34 minus 6. Finally, so we've solved it. It's solved. So now let's just write the specific solution. So the specific solution is, in all its glory, even though we've essentially fully defined it at this point, y of t equals, so C1, which is negative 2a over, what's an a, that wasn't very clear, a over 29 plus 9, and that looked like an a, plus 9, times e to the negative 2t plus 3a over 29, over 34, minus 6 e to the minus 3t. So this was c1 e to the lambda 1t plus c2 e to the lambda 2t. Now we're plugging in our solutions for c1 and c2 and lambda 1 and lambda 2, plus a over, another a that looks like a 9, a over 986 times negative 19 cosine 5t plus 25 sine 5t. Boom. And that's it. That's the whole thing. I almost fit it on there. So that's the entire solution, the specific solution. So 4 steps. I like this diagram. I mean, granted it was my diagram, but I guess it was from lecture 2. This diagram. So let's revisit it for a moment. The ODE, the forcing function and initial conditions. This is what you start with, right? The ODE gives you the homogeneous solution, and from the ODE and the forcing function, you can get the particular solution. You do have to check, the reason there's an arrow here is you have to check to make sure that it's linearly independent. You don't have to multiply your particular solution by t or anything. Then, once you have those two, they sum to give you the general solution. Finally, to get the specific solution, you have to bring in your initial conditions as well, and with the general solution and the initial conditions, you have the specific solution. You're done. So that's the whole thing. I hope that you have tracked through, done all of the exercises thus far, and there are exercises in this last lecture too, lecture 5. So please go ahead and do those. I gave initial conditions and forcing functions. I used the same equation, so the same differential equations as lecture 4's. So once you've done lecture 4's exercises, you'll have the homogeneous and particular solutions. So you should be all set up to do the lecture 5 exercises without having to redo the homogeneous and particular solutions again. So give that a shot. Answers are in the back of the book. So if you go down to Appendix A, you'll get those. And you can, obviously, if you're one of my students at St. Martin's, feel free to contact me in any way. If you are somebody from outside St. Martin's and you have any questions, feel free to drop a comment in below, and I'll try to answer them any way I can. So, all right, it's been fun. I'll see you in a few weeks. Enjoy the rest of your summers.